Okay, so I've got a problem up here. C is going to be the unit circle oriented counterclockwise. My vector field f is going to be y2x, and I want to evaluate the work integral of f around C. We're going to do it two ways. First, just as a line integral using the definition of work, and second, using Green's theorem. Okay. Of course, we should get the same answer either way. Okay. Now, if I'm going to do this as a line integral, then I need to parameterize my curve. So r of t is cosine t sine t. T varies between 0 and 2 pi. That's my standard orientation for the unit circle oriented counterclockwise. I'm going to just write up here in this corner that f is y2x, because we'll need to remember that when we come to doing this that second time. Okay, so if I integrate along C, f dotted with t ds, I know that's going to be the integral from 0 to 2 pi. I need to take my vector field and I need to write it in terms of r of t. So y is just sine t. 2x is going to be 2 cosine t. And I'm going to dot that with r prime of t. R prime would simply be negative cosine of t, negative sine of t, comma, cosine of t, dt. So that's going to be the integral from 0 to 2 pi. I'm going to get negative sine squared t plus 2 cosine squared t dt. So it looks like we're going to be using our double angle formula for cosine for both of these parts. So integral from 0 to 2 pi. Sine squared, well, I've got negative, but sine squared would be 1 minus cosine 2t over 2 plus 2, so that was a negative there, 2. Cosine squared is 1 plus cosine 2t over 2, and we're integrating that dt. I'm going to go ahead and just distribute the negative here and distribute that 2 so that it cancels here. So I can see that what we are getting then is the integral from 0 to 2 pi. I'm going to get negative 1/2 plus cosine 2t over 2 plus 1 plus cosine 2t, and we're integrating all of that with respect to t. So I distributed the negative and the division by 2 in this first piece. That's going to just allow me to consolidate my constants and my cosines of 2t. So I've got the integral from 0 to 2 pi. 1 plus a negative 1/2 is just 1/2. Plus, let's see, that's a full copy of cosine 2t and a half of a copy. That's going to be 3 cosine 2t over 2 dt. I think I'm going to just factor out a 1/2 since that shows up in both terms. So I can say this is 1/2 integral from 0 to 2 pi, 1 plus 3 cosine 2t dt. All right, so let's do a u sub. We'll let u equal 2t so that du is 2 dt. So of course that means we need to introduce a 2, counterbalanced with a 1/2 on the outside. And so now we've got on the outside 1/4. The integral from, now it's going to go from 0 to 4 pi. 1 plus 3 cosine u du. So that's going to be 1/4 u plus 3 sine u evaluated between 4 pi and 0. So that is 1/4 of what we get at 4 pi minus what we get at 0. At 4 pi, I'm going to get 4 pi plus 3 copies of 0. And at 0, I'm going to get 0 plus 0, so just 0. So we're getting a quarter of 4 pi. We're getting pi. All right, so I'm going to just write down that that was our answer. That's what we got doing it as a line integral. Not super super terribly horrible, but we did have to integrate sine squared and cosine squared. Not super difficult, but a little bit tedious. Let's just see what happens if we do it using Green's theorem instead. Okay, so the integral along C of f dotted with t dt, according to Green's theorem, is going to be the double integral over d of something dA. Now, D is going to be the region that's enclosed by C, so that's just going to be the unit disk. Because if C was the unit circle, the enclosed region is the unit disk. To see what goes here, I'm going to just remind myself of this shortcut, that it's going to be the determinant of this 2 by 2 matrix. Partial x, partial y, and then I put the two functions here. Of course, if I embedded in free space, I'd have a partial with respect to z and a 0 here, and then I'd be calculating the curl, because I'd also have an ijk. I'd actually be calculating a vector. This 2 by 2 determinant is the k component of the curl of the embedded vector, which ends up being what I get when I dot with the unit normal vector, because it points straight up. Okay. So that's just 2 minus 1. Oh my goodness, that's lovely. So this is just the integral over d of 1 dA, which would just be the area of d, which would be pi times the radius of d squared. It's the unit disk, so the radius is 1. We just get pi. That's what we got doing it as a line integral, but in this case, because this integrand, which was basically the partial with respect to x of q minus the partial with respect to y of p, where I name my component functions p and q, this ended up being so simple because it was just a constant that the double integral was a little bit faster, maybe a lot faster, than the single integral. Kind of neat to see.